What is up, everyone? Hopefully this finds you all well and healthy, and hopefully working on a little stoichiometry. So we've gone over mole to mole, we've gone over gram to mole and gram to gram, and now what we're going to do is we're going to start looking at some of the volume problems. All of these need the molar conversion, which comes from your balanced chemical equation. But the cool thing about volume is we use that other conversion factor, if you'll remember, that 1 mole of any gas at STP, standard temperature and pressure, is going to occupy a volume of 22.4 liters. So now I'm going to show you the first problem to the worksheet that I'm assigning today. This is Stoichiometry worksheet number 3. Volume conversions, okay? So let's just take a look at this very first problem together. The first problem reads, methane burns an oxygen gas to produce carbon dioxide gas and water vapor. What volume is measured in liters, of carbon dioxide gas is produced when 3.2 liters of oxygen gas are consumed? And it says assume STP. Cool. We're under standard temperature and pressure. This is going to be fun. Okay, so now what I'm going to do is I'm going to work the problem on my easel for you, okay? So here's what we're going to do. Methane. I don't know what methane is, Mrs. Fangani. I have no idea what it is. You have this awesome thing that you've been using now for, what, 6 weeks? I'm not even sure how long it's been. 8 million years? Pretty much. Google! All right, so when you Google up methane, you will find that methane is CH4. That is methane, okay? Methane is CH4, and it burns in the presence of oxygen gas. So CH4 plus O2, and it says that it's a combustion reaction. We know that combustion reactions yields CO2 and H2O. Cool. This is the very first part that you always need to start with, and that is a balanced chemical reaction. This is your recipe, and this is the recipe you need to follow with. So now we need to balance it. All right, so let's take a look. Let me get a different color here because different colors are always fun. You can thank my daughter Lainey for videotaping. I'm sure it's stellar. Okay, so now here we have our reactants. Here we have our products, okay? On this side, we've got 1 carbon. On this side, we have 1 carbon. On this side, we have 4 hydrogens. On this side, we have 2 hydrogens, okay? On this side, we have 2 oxygens. On this side, we have 3 oxygens. Now remember, in combustion reactions, you always wait to balance out the oxygens for the very last thing to do. Okay, so 1 to 1, we're good on carbon. Hydrogen, here I have 4, here I have 2. What's an easy fix? It's to put a 2 here. When I put a 2 here, now I have 4 hydrogens, but then I also have 1, 2, 3, 4 oxygens. So it changes that 3 to a 4. Cool. Well, that's nice because this is 2 here because oxygen is a diatomic. So what I need to do then is I need to put a 2 in front of this oxygen, and that now gives me 4 oxygens. So now I'm at 1, 1, 4, 4, 4, 4. I am balanced. So this is my balanced chemical equation. Boom. All right. That's our jumping off point, our starting point. Oh, you just look up my nose? That's cool.
No, I didn't.
All right, sweet. Hopefully there's no bugs up there. All right, so now what we need to do is let's take a look at the problem. The problem tells us that what volume, again, remember volumes in liters, of carbon dioxide gas is produced when 3.2 liters of oxygen gas are consumed. So we're starting, this is what we're given, this is what we know, 3.2 liters of oxygen gas. So that's where we're going to start from. So up here, we've got, I'm just going to put this up just a little bit. So we know that we have a lot of things going on here. Okay, 3.2 liters of oxygen gas. Okay, I need a black marker. And then I gotta make my railroad tracks that you love, okay? I don't know if I need it that long, but that's how long it is. All right, 3.2 liters of oxygen gas, and I know that that conversion factor, that 1 mole of any gas at STP, and it said assume STP, is gonna occupy 22.4 liters. Okay, so this is a way we're gonna get rid of those liters and get to moles. So 22.4 liters of O2, 1 mole of O2. Okay, so now liters of O2 are gonna cancel. Now we're at moles of O2. All right, so now, my black marker, make it look good. All right, so now what we need to do is we need to go up to our balanced chemical equation and we need to take a look at that molar ratio. So we're going from moles of oxygen consumed to liters of oxygen consumed to liters of CO2 produced, okay? So what we need to do is we need to look at the ratio in this balanced chemical equation of oxygen and CO2, because those are the ones that we're dealing with in the problem. Now, from the balanced chemical equation, I know that for every 2 moles of oxygen gas that are consumed, I'm going to produce 1 mole of CO2 gas. Can you guys see that? For every 2 moles of oxygen that are consumed in the reaction, it's going to produce 1 mole of carbon dioxide gas. Cool. All right. Now let's take a look at our units. How are they shaken out? Well, if I take a look here, now moles of O2 cancel. Now I'm at moles of CO2. But remember, the problem wanted me to get to volume of CO2. So now I need to go from moles to liters, and luckily I have a really handy conversion factor that I know that talks to me in liters, and that is that 1 mole of any gas, and in this case 1 mole of CO2, and it's again assume ATP, is going to occupy 22.4 liters. Okay? All right, so now let's check these units. How are our units going? Well, let's see, moles of CO2 will cancel, and then we're going to get liters of CO2, and we want liters of CO2. So now what we're going to do is we're going to run the math, and once we run the math, you're going to get an answer of 1.6 liters of CO2. This is our answer. And I got that because I took, on the top in the numerator, I took 3.2 times 22.4. I figured out what that was. And then I divided that by 22.4 times 2 on the bottom, okay? And that's what's gonna give me this 1.6 liters of CO2. All right, so if 3.2 liters of oxygen gas are consumed in this combustion reaction, we will be able to produce 1.6 liters of CO2. All right, so hopefully that helps you in solving these problems. Let me know if you're having issues with mole to mole or gram to gram, because I can easily walk you through a couple of those problems as well. All right, so once we get this down, then we're gonna move into some really fun stuff, which is limiting reactants, and it's pretty cool and pretty fun. So hope you guys are all keeping busy and staying healthy. All right, take care. Let me know if you have any issues. Have a good day.